This is part one engineering mindset of the series AI for Everyone. Let us explore how the engineering mindset has unlocked and translated the logic into mathematics. Mathematics serves as the universal language through which humans have taught machines to interpret, process, and execute complex logic. By transforming abstract concepts into mathematical representations, we enable computers to operate in ways that mimic human reasoning. We will explore the historical and conceptual breakthroughs that underpin this process, with practical examples that illustrate the foundational role of mathematics in encodings in computing and artificial intelligence. Some of the examples we will explore are Morse code, binary numbers, barcode, and GPS. We will then begin our journey to explore the world of LLM. Let's talk about Morse code, the language of sound. Morse code was developed in the early 1830s by American inventor Samuel F.B. Morse, with assistance from Alfred Vail. From beeps to Morse code, one of the earliest examples of translating logic into mathematics or encoding can be observed in the development of Morse code, a system that revolutionized long-distance communication in the 19th century. Samuel Morse had an idea that using just a sound of short and long beep, he can represent alphabet and numbers. This translation of various combination of short and long beep allowed him to transmit characters over electric wires. Prior to this, the only way to communicate was to physically send the handwritten letter, which were picked up by letter carriers on horses, and it could take days before the receiver receives those handwritten letter. But due to this technological breakthrough, messages can now be sent to the other end in a matter of minutes. This initial electrical signal were sent over physical electrical wires, and to support this transmissions, a large networks of wires were laid down across US. This is an example of how someone had an idea that we can represent characters as different combinations of electrical sound, which can then be transmitted quickly across the other end. The chart here shows representation of each character to respective combination of short and long beeps. Let's listen how some of the characters sounds as Morse code. Now let's also listen to how the actual transmission used to be. Now let's talk about barcode. Norman Joseph Woodland and Bernard Silver were trying to create a system to rapidly capture product data at a checkout counter in grocery stores. Woodland, who had learned Morse code as a Boy Scout, reportedly drew on the concept of dots and dashes, imagining them as elongated into parallel lines. He famously recounted that he was on a Florida beach, thinking about how Morse code used short and long signals, when he dragged his fingers through the sand, extending the dots and dashes into continuous lines. So from dot and dashes, Woodland came up with the idea of representing it as thin line and thick line so that he can use camera to read them. Based on this, here is how you would write "love one another" in the form of barcode. This were the very early barcodes. Barcodes had a very rough and long history. In those days, they used optical scanners, which were of poor quality and were not very reliable, which delayed the widespread adoption, and real usage did not gain traction until the discovery of laser scanners. The modern-day barcode now uses zeros and ones, or binary numbers, to represent thin and thick lines, and was later standardized to be known as UPC barcode. So Norman Joseph represented same characters as thin and thick lines instead of short and long audible beeps or dot and dash in visual representation. This shows that same characters can be adapted differently based on intended purpose. In case of Morse code, the intention was to send or transmit the information, so converting it into electrical signal was the intention. but in case of barcode, the intention was to read. Now let's talk about what is the basis of our modern-day computers, the binary numbers. George Boole, 1854, a British mathematician, introduced Boolean algebra, a form of symbolic logic. Though Boole did not specifically tie his algebra to electronic circuits, his work directly influenced how digital circuits would eventually be designed, as they naturally map to binary 0 and 1 states. Claude E. Shannon, 1937. While at MIT, Claude Shannon showed how Boolean algebra could be applied to the design of electrical circuits using relays and switches, which have two discrete states. As we have seen in the case of Morse code and barcode, in the binary numbers, characters are represented using 8 bits in combination of zeros and ones. English alphabet A can be represented in 8-bit format as 0, 1, 0, 0, 0, 0, 1. Similarly, Z can be represented as 0, 1, 0, 1, 1, 0, 1, 0. In electronic, a transistor can store either 0 or 1, and we can use 8 of them to represent a character or number. So by having millions of transistors, we could create storage devices that can hold large amount of data. Simply using transistors does not enable us to make computers. It just helps create a device that can handle binary numbers. We need something more to make it smarter. And that's where the logic gates comes into picture, that make these transistors mimic logic, hence their name. Logic gates are made up of specific type of arrangements of transistors. As you can see in the picture, there are 8 types of logic gates, and when you further arrange them in specific chain, you get a computer that we are using nowadays. So microprocessors are generally made up of billions of such transistors and gates. The more the number of transistors, the more powerful your computer is. Contrast this to Morse code, which wanted to transmit signal across distance, used audible tones to represent characters, to barcodes, which want to read numbers optically and use thin and thick lines, to now, the computers, which actually want to manipulate or process the information itself and is using transistors and logic gates to process the characters and number. So as we can see, the same characters of language are represented and manipulated differently based on the intention of its usage. This is what engineering mindset is about, translating into different forms so that we can use machines to process or manipulate information. Microprocessors, the building blocks of the modern computers and mobile phones. Here we are talking about some of the popular microprocessors and how many transistors they use. As you can easily guess or see, the microprocessor that had more transistors are the most powerful ones. Here is another example of an engineering mindset, which takes a different approach from the one we discussed earlier, as it does not deal with characters at all. I wanted to include this example to show that translation or encoding is not limited to characters. It can apply to many other concepts. In this case, we are talking about how someone had the idea of overlaying virtual lines called latitude and longitude over the physical Earth. By doing so, we can use mathematical formulas to navigate the Earth's surface, ultimately leading to the development of GPS navigation systems, which we rely on today. An essential formula in this context is the Haversine formula, which calculates the great circle distance between two latitude-longitude coordinates on a sphere. This formula is key to GPS navigation, allowing us to determine distances between known locations. Now, a common question arises. How did we draw latitude and longitude lines if they are not physically visible? I don't see these lines in my neighborhood, yet I can still use GPS while driving. This is a great question. The answer lies in the fact that latitude and longitude lines are a human-made virtual reference system, not something physically present on the ground. These lines exist conceptually as a coordinate grid system to help us pinpoint locations. GPS devices use signals from satellites in Earth's orbit, specifically the Global Positioning System GPS satellites, to triangulate positions based on this coordinate system. Thus, while we don't see these lines, they are fundamental to how modern navigation works.